Anyway, thank you, Adrian. That was a really nice introduction. So it almost takes away the need for my first slide. That's a lot of repetition. Just briefly, my research interest is applying deep learning to computer vision and robotics. And personally, I'm really interested in building systems that require minimal human intervention and in the end becoming help to the people who use them. That partially motivates my interest in applying intelligent vision systems for the visually impaired, for the blind, low vision. This actually motivated me to move across the country from Boston to attend UC Santa Cruz, because my research group there is one of the few in the country that actually specializes in this research. So, and last summer I joined Magic Leap as one of their first deep learning interns, and I've kind of paired my graduate research with my work there, and it's been phenomenal. So, okay, who kidnapped a robot? Has anyone here heard of the kidnapped robot problem? Yes. Anyone else? Okay. It's good to get an idea of what your audience is familiar with. So, what is the kidnapped robot problem? In the kidnapped robot problem, a robot is unable, it's a very canonical problem in robotics. It's basically in this problem, a robot is unable to estimate its own position after it has been moved to an arbitrary position. So the idea would be, you have a robot rolling through its environment, mapping it along, and someone comes along, picks up the robot, and drops it in another location that's kind of nearby, but not anywhere. It doesn't really know where it's been dropped to. In a less friendly manner, someone just says they kicked the robot, and the robot loses track of where it is and then needs to relocalize. So often the robot may have access to a map of this tracked environment with images, maybe 3D data, IMU data, and it leverages all that information in order to be able to relocalize its position. So this down here is just a typical example of a robot map that's built with probably a LiDAR system. But in this map, and this will be applicable to what I talk about after, you can see that this robot has, mapped a whole area with a foyer, living room, like the whole building, which is actually applicable to the problem I'm working on. So to clarify, what is relocalization? To localize means to establish locality. I know where I am at a given point. Just think of your GPS, you know exactly what latitude and longitude you are, what heading you have. However, if you're the poor robot that gets moved, the robot needs to relocalize, which means it needs to require that knowledge. In the robot world, position isn't always measured in GPS. It's measured in a 6-DOF pose, which is basically like an XYZ pose and a yaw, pitch, and roll. So that's why it's called 6-DOF. So anyway, so when I relocalize, I reacquire this knowledge of where I am. And like I said, this usually occurs during tracking failure. And relocalization is hard. So when you don't know where you are and you have sparse information, another way people like to say is, like imagine you're in your home, but someone spins you around really hard, and then you open your eyes and you have to figure out where you are in an instant. That's kind of what the robot's trying to do. So robot mapping. A typical robot has multiple sensor modalities for mapping and tracking. This is an artist's rendition of the Mars rover prototype. This robot has, stereo sensors, IMU, infrared, inertial sensors, Kinect. A lot of university-level research robotics uses the Kinect sensor, so they use the 3D data, the images, or they call it RGBD data, to do this relocalization that I'm talking about. So robot mapping most often is done using SLAM. SLAM is called Simultaneous Localization and Mapping. And it means that the robot is continuously building a map of its environment, and thus the mapping, and it's also keeping track of its position at the same time. So in this problem that I'm working on, we focus on using visual tracking only using a single camera. So unlike our Mars rover that billions of taxpayer dollars have funded, we are using a single camera, high-resolution camera, to do our mapping and tracking. And we also call this Monocular Camera. But some feedback. So, like I said before, the relocalization process is the recovery process for when we have this failed tracking in our SLAM system. So, let's see. I have a video that kind of gives an overview of what SLAM typically is, but I can walk through also. So, for example, if I were using this phone to do SLAM, and believe it or not, people can do robotic SLAM mapping on an iPhone, which is pretty remarkable if you think about it. What you're doing is you're maybe panning your camera around, and you're using some sort of advanced vision algorithm to build a map of the world around you. So that's kind of what this would be. These view frustrums are your camera moving around, and you have some notion of what your pose is. So from your previous frames. So every time I move my camera, I add something called a new keyframe. So that's the new image, and the keyframe gets sent to some server. The server can localize me within the map, and they have several more advanced vision algorithms like bundle adjustment, feature mapping, feature matching, etc. that does this. And basically, it does like a 2D to 3D match, it kind of depends on what your sensor is. Then you align to some global model, and you get the new position of your camera. So, and that's what the pink is. So, okay. So what I've been trying to establish with this background is there are old ways and new ways of doing things. The old guard, the new guard. We're the new guard. So typically, mapping, any sort of mapping or stereo processing, because a lot of this also uses stereo processing if you are trying to do true 3D, uses old school, like non-deep learning methods of computer vision or SLAM. So the move in computer vision right now is to move away from these kind of handcrafted features that you find that are typically used to do these feature matching when you use like feature matching. So you have some frames from where you were before, you have a new frame, you want to match what you saw previously to the new image. So typically you'll extract something like SIFT or SURF feature, or if any of you use OpenCV, ORB features are very popular. You'll select features from one and another. You'll try to do some sort of, use ransack and do matching and get like a transform from one to the other and so on. So it's, like I said, we call them handcrafted features because they're highly engineered features to only work with specific types of textures and environments. And one place where they typically fail is if you have a room, like this room, for example. If I'm relying on an algorithm that needs to do edge detection and corner extraction, well, there's not a lot of texture on these walls. And I'm not going to stare at the ceiling to do localization and SLAM. So we're trying to introduce new ways, new deep learning methods to sort of bypass these kind of traditional methods. I have a video here that is just an example of using FastSLAM, which is another very popular way of doing this robot mapping right now. I'll show you. And this uses the existing sort of typical feature matching. So you'll see as this car. Let's see. Oops. Okay. I don't know if you can see, but basically right now Think of the Google vehicles you see driving around Mountain View. This could be them with, like camera sensors mounted on. They're doing feature tracking. They're using maybe some sort of visual odometry, which is meaning they're estimating the evolution of the camera from frame to frame. That's why you get these vector fields. But down here, the sensor is building up a map of the environment. So in this particular data set, it's called the Kitty data set, and they're driving through the residential streets of some city in Germany. So anyway, the point being is that feature mapping works well in these very rich environments, but imagine you had a situation where the car was driving under high blur situations, then your feature matching goes out the door. Or if you wanted to build a model of this that you wanted to say, I'm going to use relocalization. Let's say your car stops, you went into some sort of tracking failure mode. You had to restart again. So in order to do that, I have to build a ginormous map of this environment. And if I tried to maybe do some sort of relocalization based upon visual appearance, then you'd have to train a really large model to extract features over this and kind of build a bag of words vocabulary in order to do that. Okay. So I guess my point in saying all these things is that most of these approaches are feature matching based, and they're not very extendable to large scale areas. I could train some sort of deep learning algorithm to maybe be able to recognize things in a small environment. I can recognize that kitchen, I can recognize these chairs, but the problem is those methods tend to fall apart once you move into much larger scale areas. So if I train some sort of recognition model, like something like that, like I said, uses a bag of words feature extraction approach, you build a visual vocabulary of the environment you're in, and once you move out of this room and into the offices maybe next door, that if I wanted to add that vocabulary to the robot's brain or to its map, then you have to retrain on all the new areas that you see over there. So it's a very kind of brittle process. Basically, I'm saying that the way systems are right now is they don't extend very well to multiple areas, large areas. In deep learning, if any of you know anything about the work that's been done with deep features, you know that the features are very generalizable. You take the FC7 layers of AlexNet and you can use them to do image recognition or nearest neighbor search or anything like that, just by passing your image through this network that has not been seen by the before. And you just extract these generalizable features. We're kind of moving in the same direction and using this approach to do relocalization. So back to the problem of relocalization. Relocalization is a very important problem, but it's just like sort of one box in the flowchart of SLAM, if you will. But without relocalization, the tracking would fail. So the next step is, well, okay, we know what the problem is. If a robot gets lost, would it be possible to use a visual recognition approach for doing relocalization? So what we're saying is, can we use a single image as a query against our perhaps sparse SLAM map to get the best estimate of position? So you can see in this kind of higher level picture, you have a car that's somewhere and it's querying all these different locations of where it might be in the map. And as you can see, this particular example covers a fairly large area. It looks like it's the whole campus of a university, perhaps. But still a powerful concept, given the large scale of the area. So the idea using this and is that once you have imagine you had this, hopefully this image is, I can explain this. This example is taken from the Microsoft 7 Scenes dataset, which was a dataset collected with a Microsoft Connect. And what they did was Microsoft Research created this what is now a standardized data sets, and as anyone in deep learning will know, that data is extremely important. Good data is extremely important. And anyway, so we're using this data sets which have 7 scenes, and each scene has 2 or 3 different trajectories of the Connect. So imagine the Connect has collected a movie like 2 to 4 times for each scene. And the trick is to be able to use one of those trajectories as sort of a training data set. They call it train. And you have another trajectory, which is your testing one or your querying one, and you're trying to relocalize one to the other. So you want to say, okay, I'm at this position now, given all these this other recorded data, which is effectively your SLAM map, what's the nearest position for me? And if you can come up with the best answer, if you find the best closest frame, then you can use that as an approximation for relocalization. So this is an actual result that I have, which I'll talk about in a few minutes. But basically, this is from a scene called Heads, because it has all these heads. I don't know why people keep these heads on their desk, but anyway. As you can see, this is a 3D rendering of the point cloud that the Connect generated. And this is the query trajectory that's my kind of test query. That would represent the active path of the robot currently, and then maybe it gets lost. And this green represents all the mapped images it has stored somewhere. And so you want to be able to take this query image and map it against the top 5 nearest neighbors for relocalization. So just to emphasize, the query image came from the red and the green came from this green. So that's, in some points in this, it looks like they're pretty close, but if you're at some point in space and you have, previous camera angles that have been all around here, it becomes a really difficult problem to figure out what's the best. And you need a really high precision algorithm to be able to do that. So, finally, deep learning. So this is my project. So I am applying deep metric learning for relocalization. And the idea behind this is can we teach a deep neural network to learn a lower dimensional manifold representing places and locations by showing it images that should be similar and those that are dissimilar. So, for example, in this triplet of images, the unit of images we use to train these networks is coincidentally called triplets. But anyway, we have a set of 3 images. So we want to select images for the input of our network that are similar. So the top 2 are similar. They happen to call one the anchor image, like that's just the anchor you're starting with. Then you want to pick an image in your data sequence, in the same sequence, like one of those red or green, that is similar. So this is in this particular data set, the car is just driven up the street a couple of hundred of feet. And then this image is completely different. It was taken at a completely different location. So to emphasize, this process is called metric learning, where an L2 metric distance is learned between each scene class in each scene. So to emphasize, the metric part is the distance part. It's also called metric distance learning too. So how this works under the hood is basically you're training a network to project go from image space into a manifold space. And what you're doing basically is you have this high dimensional space that is here, and you want to be able to represent it in a much smaller, compact, normalized form. So for example, the triangles and the circles and the red and blue circles, those could be pictures of, or parts of trajectories from your video sequences. Like maybe you have like one part of a neighborhood where the car was driving through. The red might be another part of the city. You have all these different things. And when the network is learning in all of its coefficients is this linear projection. So then you're basically taking that data and you're making a nice alignment of it in this lower dimensional space. So practically speaking, what this means is I'm able to take a network, have an image, I can take my high resolution image and project it into a 128 element feature vector, and that's it. Consider the significance of this for doing real-time anything, real-time search, real-time nearest neighbor search, storage. It's pretty significant. So that's why I'm really excited about this research, because it can make a lot of things happen. Image storage is a huge problem. It's tedious and it's slow to load images, and there's all sorts of problems with it when you're trying to do real-time mapping. So, this is a case study for using metric learning. I don't know if anybody is familiar with the paper FaceNet. FaceNet uses metric learning to learn, to do basically person identification. So basically in the learning, well, first of all, I'll start with the structure of the network. Remember I mentioned there were these triplet of images. So this is your deep learning network that you actually use. We call it a triplet network. So, and the idea with this is it's a network that has 3 towers. Each tower corresponds to one of those images I told you about. It has an anchor, it has a positive tower, and then it has a negative tower. Now, the structure of these towers is identical, meaning they all have the same number of layers, the same types of pooling, et cetera, et cetera. And when you train and you have your loss function and then you do your back propagation, the loss is actually averaged by 3, or it's divided by 3, and the weights are tied, so all the weights are shared. This is a variation on a Siamese network. Some people call it a Siamese triplet network. For simplicity, I just call it a triplet network. But at train time, you basically train with 3 images all at once, and then you are basically, for each network, for each tower, you're extracting this 128 element embedding that I mentioned. So this 128 dimensional feature vector is called an embedding. This is called a manifold, but some people call it embedding space. They're basically the same thing. It's just a matter of terminology. So in this particular case, you're extracting and embedding this 128 feature vector from each of these towers. And then you're doing you're doing an L2 distance. You're calculating the L2 normalized distance between the positive and the anchor. So you're getting that metric distance between these two that's a measure of similarity between these two. And then you're doing the anchor negative distance here. So that's your measure of dissimilarity. And then what you do is you basically pass both of those into your loss function. So basically the loss function sees the anchor positive difference, and then it sees the anchor negative distance. And within FaceNet, they use a softmax function to compare them. I'm sorry, normalize to the top nearest neighbor images. So So there's two concepts here. So the idea is that, okay, maybe I have, this is just a sort of abstract representation of the embedding that has occurred because of the training data. So this is representative of a projection. But if I have a map that could be these images, let's say, and there's an embedding 128-dimensional feature vector for each of them, I can come back, run my query image through the network, and be able to relocalize really quickly and find my nearest neighbor and find the closest scene to where I am. So this is the goal of my research. Basically, I want to go from that small scale embedding, smaller is always easier, and extend that to a large area. So instead of just having it in one, okay, the chess scene's not in here, but I want to be able to say I can train an embedding that knows the visual similarity and dissimilarity between all these different areas, and there's a direct relationship between that. So in this embedding space, we're saying there's a direct correlation between that and real world space. And so we'd like to be able to train an exact model like this. And one of the really powerful ideas of this is that you should be able to train this in, let's say you did it for a house. Be able to train it for one house once, put it away, put all your computers away, have your embedding, your network, and you just go to another house and you're able to do the same relocalization there, assuming you're building up a map in that environment. So this is called, in that case, it would be called zero-shot learning, because you train once and you never train again. Unlike, you were saying deep face uses, what is it, cross-entropy normalization. For them, they have, let's say, 1,000 identities in their network, in their database. Okay, they train a network, they invest the time. Then they add one more employee. Then they have to retrain all over again. If I add another room to my house, assuming it's within the general parameters of what a room is, 4 walls, stuff in it, I don't have to retrain. And the same thing for FaceNet. The power of FaceNet is that it can extract, it can be used for lots of different faces without retraining the network. You can extract this embedding for anybody, unique embedding for anybody's identity. So, so additional requirements. Real-time localization must be fast. If you're a robot doing fast mapping, moving through an environment, you get lost and you have to find where you are really quickly. I mean, you have to be able to search over some search space really, really quickly. Thus, the 128-dimension feature vector that I mentioned is really powerful for that. The deeper localization requires a fast and compact enough network to work on small, mobile, power-conscious platforms. Any sort of, let's see, NVIDIA has the Tegra, Tegra X1 chip right now that you can do deep learning on, and they use it in their new driving car prototype. This could be a good candidate for that. But, maybe eventually something like this will be moved to a high-end iPhone or something like that. 10 minutes? Okay. Anyway, so we basically want, a lot of these deep networks are very large, but we want lightweight networks that are very powerful and small, and won't be CPU hogs. And I mentioned zero-shot learning, be able to train once and put all your training stuff away and be happy with that. So that is it. So thank you for coming. I just wanted to say that I apologize for not going into the details of the network, but my work is about to be published, so I can't divulge those details yet. But, yep.
Is it possible, before you ask a question, you know, I can just remind everybody when you ask a question, then we can try to give you a mic so that you can try to talk into it. But also, it's very helpful if you stand up and just kind of introduce yourself. So you just say who you are and I don't know where you're from or anything like that. That's very helpful so that when networking afterwards, people will know you.
We can go two at a time so that we always have a mic heading to the next person. So if the next.
Okay, I'm David. I'm working with point clouds mostly, and so currently far from deep learning. But I hope I'm going into this area. So my question is it possible to use your approach for relocalization on not previously learned scene? Like you started in this position, you started collecting pictures while with using whatever SLAM you like, like you showed before with feature mapping SLAM. And then using that collected previously pictures, is it possible to relocalize if you lost?
So are you asking, can you do relocalization like this for point clouds, or?
No.
Okay.
No. If I understood right, your approach requires to explore, to previously collect pictures of the whole scene, of the whole working area, to be able to relocalize in any unknown place. Is it possible to start without this, without collecting the pictures, but using pictures collected previously on along my trajectory, in your red trajectory?
Right. So it is not possible to relocalize for this approach, without a previously extracted map.
One more question. In your approach, what is required for initializing the system? You need collect pictures of the working area and the locations from which they were taken, right?
Right. So there are different levels of relocalization you could do. You could simply take a video of an area and say which image is the closest image to this. If you happen to have the pose data or even GPS data, if you're thinking of it in terms of a driving problem, you would have to associate that pose with that image. You would do the nearest neighbor search and try to estimate where you are based upon that. So yes, to initialize your system, you need to have at least one image with one set of pose information. I hope that answers your question.
Next question.
So I'm Ben Reinhardt, I'm with Magic. You train on both the rotation and translation error of the estimate the closest to the nearest image. You have, like, it's a classically tricky problem to normalize between rotations and translations. How do you attack that?
So can you clarify what you mean by normalize between rotations and translations?
So at some point you need to say, like, how bad am I? And you're some amount of bad in rotation and you're some amount of bad in translation.
Right.
But they're completely different units, and so how do you stick them together?
I see. Well, currently, if you read the literature, even for papers on relocalization using deep networks, they currently evaluate them separately. So there's a paper called Camera Relocalization with 6th Degree of Freedom Pose, and for a given scene, they're able to regress on pose directly using an image. And regress on pose, I mean, for a given image, they're able to estimate its pose directly. The thing is, they're only able to do that over one scene, and it requires training data for that one particular scene, so it's a little bit brittle. The way they evaluate the goodness of their algorithm is that they take the median pose in each, so they'll take the median rotation and the median translation, and it doesn't work very well because when you want to relocalize, you don't want to say, okay, this image is the best translation, but this image is the best rotation, because you have to pick between them. The way my approach is better is that because we're using this embedding space, the L2 distance in this manifold embedding space, we can find the nearest neighbor and pick the best and hopefully the best in rotation and translation. So I'm not sure if that makes sense, but I can point people to paper. No? So currently there is no way to say, okay, take the translation and the rotation error and put them together into one number and give me how good it is. Like, that does not exist right now.
So how do you decide which one's the nearest neighbor?
So the way it's all in the embedding space. So this 128-dimensional feature vector, I just take the L2 distance between everything in my search index, and then I take the one that's closest.
When you're training it,
When I'm training it,
how do you call it which one's better?
we're not telling it which one's better, per se.
They're comparing the marketing acceptance. Pose is something that's just added on. Maybe this question is as well with that relation.
Yeah.
Let's move on. I think I understand the question also. We're going to take a little bit of
Yeah.
to get to the bottom. You have the mic.
Hi, my name's Vaibhav. So I had a question regarding just, you mentioned that these data sets were collected using Microsoft Kinect.
Yeah.
Are you only using the image part of it? You're not using the
I'm
object?
only using the image
You're
part
only
of
using the
it.
image part,
Yeah.
so, okay, that was it. Okay. The next part of the question was, and just to clarify on this point, so essentially you find the nearest neighbor match of sorts,
Yeah.
quote
Yep.
unquote, using your methodology, and then you just return the pose and translation from there.
Yeah.
Would that be correct to say?
Well, the pose,
You don't
yeah.
interpolate or regress or anything?
You could interpolate. I mean,
Sure, I'm just saying what's
Sure.
done now. Right. Next part of the, just very quickly, last part, you took this anchor image and negative and positive.
Yep.
So wouldn't the learning greatly depend on the distances between the anchor and the positive and negative? So you would have to be carefully select
Yes.
to give it the
Yes.
right kind of,
Yes.
right? It
Yeah.
would have. So how do you decide on that? And do you just do one-shot learning, or am I misunderstanding this?
We're doing zero shot.
Zero shot. okay.
Zero. I mean, you can call it one shot too.
Yes,
No, I mean it depends. It's all.
Sure, but the
Yeah.
point is, do you give it only one example? Let me make it more explicit. Do you give it only one anchor, positive and negative, and that's it?
Oh no. I mean, like, so the triplets are only for training time.
Right.
So, and the selection of triplets is incredibly important. And
Yes. So,
So-
how do you do that? That was what I was interested in.
Yep.
Yeah, that's why I
Yep.
asked that.
so, like for the Microsoft 7 Scenes data set, you would pick images that are, you'd want to pick generally 2 images that are within like for example with a camera, maybe have the same amount, have a certain amount of field of view overlap. And then for the negative, you'd pick something of a different class. So the reason I use FaceNet is because it's a really easy way to understand. For the training, they use the identity of one person. They'll select one image in the person's identity index, and then they just pick another of that person, like maybe the person's looking to the side or something, and then they'll pick a completely different person as the negative. So, and you need to show the network enough variety of those triplets. You can't just show it like a very narrow, like 2 images with only like 30 degrees field of view separation between them. You have to show it a range.
I get that.
So.
But this is something you're saying how you would do it manually, but ultimately for some sort of large scale, it would have to be some sort of an automated process of selecting these triplets.
Well, it
That seems
depends.
kind of non-trivial. That seems like a chicken and egg problem to me. How do you select those triplets?
Right. So you
without
have
having
to.
an
I mean,
embedded
you have to pick them based upon a certain similarity, and each paper does that differently. I have my own. Basically, I'm looking for images that are similar within a certain tolerance. You don't want them too similar, but too dissimilar. Too similar, but too They have to be within a
Those are
certain
the
range.
heuristics that you're quoting me, but
Yeah.
how do you actually...
So my heuristics are, for example, I've looked at using spatial pyramid matching.
Okay.
And you can, for a given image, you can get you can calculate the histogram. I'm giving you a very specific example.
Okay.
For histogram matching, for the spatial pyramids, which is I used it because it's very easy to run in MATLAB, and I downloaded it. You have a metric, a value, which is the histogram intersection between the features for the image that you're querying and all the images in like a sequence of images. And you look at the ones that have the highest degree of similarity. Like you have to look at, there's a certain amount of heuristics in that. Sure.
Hi, I'm Mona, and I'm working at Mercedes-Benz. One of the problems with SLAM and localization is that it's the main drawback is that the changes in the environment, like seasonal changes, rain, night, really affect the localization. How well changes in the environment in your case will affect the method, how well you can perform when there are some changes in your images.
So what you're talking about is place or appearance-invariant recognition or relocalization. And how well this happens all depends on your training data, like how much you show it. If I only show my network the data set I showed you, which is all nicely lit interior images, it will probably only perform best under those conditions. However, if you show it data from a mixture of cases, like an intersection of traffic in the rain, I'm sure you're probably using those traffic cameras, and you're using in the rain, in the sun, at dusk, dawn, etc. It becomes, the more you show it, the more you augment your data set, the more invariant the network becomes, and can select images that are identical in appearance based upon how much data you show it. So it can become very invariant to those situations. So.
And the next question, when you're doing the projection in the lower manifold, are you using a randomized projection, or is just SVD in that case?
No, the projection is actually the triplet network. So what you're doing is when you have your deep network and you have the single tower that I mentioned, so you're using your deep network as your projection. The deep network is learning the projection between the two. So that way you're going from image space to the 128 embedding space. And so all of these embeddings that you extract are normalized. So you can think of it as you're projecting everything onto this big hyperparameter ball. So all the embeddings have the same length, but they're all kind of in this hyperparameter ball. So.
Okay, so we have time for one more question. There's someone who's been waiting for the mic, so.
I can answer questions after too.
Yeah, there'll be time afterwards to socialize with the speaker and ask more questions probably.
My name is Raj. I work for a semiconductor company. My question is similar to hers. When a change happens, right? You are telling how the ambience is, how it will affect. My question is there will be a dynamic set of people or somebody. Let's take a home, and then people are always going to move. But if you take furniture, that won't change. So how effectively that can be modeled in your approach?
So I believe what you're talking about would be called occlusions. If I have a scene and I rearrange the furniture, or if I have people walking through my scene, these networks are very invariant to that, robust to those kind of changes. So they're able to handle these situations very well. So, and for tracking, that's especially important. So outdoor tracking. So.
Okay, so let's go ahead and wrap up. Let's thank our speaker.
So, thank you.